afternoon. I'm Spot On Weather meteorologist Matthew Euler. Welcome to the How the Weather Works training series. This is part 12A. This is going to be on thunderstorms. And I do have because there was so much material, I decided to divide this topic up into two parts, 12A and 12B. Taking a look at the picture to start today's training, this is a great depiction or representation of an intense thunderstorm. And you can tell by the shape of this storm, it almost looks like it's a saucer shape, right? You notice that? Right in this location here, how it's very saucer shaped. This is an example of what's known as a mesocyclone. It's a rotating area of a thunderstorm, a rotating updraft. And I'll get more into that as we progress into the next two training sessions on thunderstorms. So let's go ahead and kick things off. I'm going to start today's training by just briefly going over thunderstorms in general and how they form. So in general, convective storms that form with rising air, these are known as thunderstorms. And convection, let me go ahead and draw it out. When I talk about the word convection, I'm talking about the case where if this is the surface, I'm talking about a case of where you have rising air motion with convection. It's in the vertical. Any vertical transport of heat and moisture is known as convection. And it's a phenomenon you get to occur. You have the sunshine out in the warmer time of the year, late spring and summer seasons, where the sun gets more intense, it gets higher in the sky. That intense incoming solar radiation is going to heat the surface, that shortwave radiation. And when it heats the surface, it's going to result in air rising in the vertical like this. So the air is rising in the vertical. Eventually what you get to occur are these cumulus clouds, these puffy clouds that form on hot summer days. And so that's what I mean by the word convection. Convection being that vertical transport of heat and moisture in the atmosphere. And as long as a rising air parcel is warmer than the surrounding air, that means it has positive buoyancy. There is an upward directed buoyant force that's going to act on the parcel. That parcel is going to continue to want to rise, being less dense than the surrounding air. Now, the warmer the parcel is, the greater the buoyant force, and the stronger the convection. Triggers for upward moving air. What causes this upward moving air motion, this convection? It can include anything from unequal heating of the Earth's surface. Terrain can also result in this rising convective air motion, or just simply lifting of the air along frontal boundaries in association with air converging in the low levels along the front. So there's many mechanisms that can result in this convection and ultimately in the development of thunderstorms. When we have diverging upper level winds and strong low level convergence, that generally tends to favor thunderstorm development. And I had a discussion on divergence and convergence in a past How the Weather Works training video, so please feel free to take a look at that for a more in-depth explanation on these two terms, convergence and divergence. So I will just briefly cover it here as a refresher. Whenever you have air streams that come together, as indicated by these two arrows, let's say this is at the surface. When the air comes together or converges, that is known as low-level convergence. And what usually happens is we get upward rising air motion in the vertical whenever the two low-level air streams converge. Once you get to the upper levels of the atmosphere, there's a certain point at which that air will diverge aloft over the converging low-level air column. And this is a very favorable condition for thunderstorms. Usually we see thunderstorms with warm, humid air in place, and that warm, humid air is going to be lifted. At times, thunderstorms occur with lower surface temperatures, believe it or not, especially along the U.S. West Coast when you get these cold pockets of air aloft moving over the region, and what that does is it increases the instability. So I want you to think about this for a moment. One of the more destabilizing factors to cause thunderstorms when we destabilize or create more instability in the atmosphere I'm going to do a little drawing here. There's many methods that can create this instability or increase it. Okay, let me go ahead and draw this out for you. The third bullet here is what I'm focused on, where you can get thunderstorms with lower surface temperatures along the west coast. So at some points in time, you'll get these closed upper level lows that just sit in the upper levels of the atmosphere. Now imagine this is the surface, the red line I'm drawing now. And so you get these cold upper level lows. So the pocket of air aloft above this surface is much colder. And whenever you get a cold over a warm situation in the atmosphere, or cow, that generally tends to lead to greater instability. And it's going to promote rising air motion in the atmosphere. Okay? So just keep that in mind. That warm air at the surface being less dense, it's going to want to rise. It's less dense, it's going to be more buoyant. Thunderstorms can also occur in winter season when you get colder air aloft moving over an area, and this can produce an interesting phenomenon known as thundersnow. And I have in the bottom right-hand image here, you'll notice that the ground is covered down here with snow, and you see this streak of lightning go across the sky during a snowstorm. And thundersnow is actually quite common, especially in more intense mid-latitude cyclones, more intense snowstorms. I've actually observed it myself back in 1987, where there was tremendous amounts of atmospheric energy in the atmosphere and instability, and we had extremely heavy snowfall rates, up to 2 inches per hour in that particular storm when we had thunder snow. One other thing to point out in the wintertime is in order to get convection in the winter, it doesn't take as great of a vertical lift to really get that instability. So in a lot of cases in wintertime, you get what's known as slantwise convection. In the summer, it's more vertical like this. So I'll just put an S next to this arrow here. This is a summertime situation, okay? And this would be a wintertime situation. And by the way, the tops of the clouds aren't really as high in the wintertime because the atmosphere is much colder and more dense overall. But you get what's known as slantwise convection in the wintertime, okay? So interesting here that you can get thunderstorms with lower surface temperatures when you get a cold pocket of air aloft here in the middle diagram, especially if you get the sun out and it sends its shortwave incoming solar radiation towards Earth's surface. This is the sun here that I'm drawing out, sending this electromagnetic waves of heat energy to the Earth's surface. So it's warmer here at the Earth's surface, represented by the W, and much colder aloft with that upper low. And a lot of times this happens in Southern California during the winter season, by the way. All right, so now let's move on to a discussion of thunderstorm types. We have air mass thunderstorms and we have severe thunderstorms, and there are two different types of storms, and we'll get more into that and more into detail. With air mass thunderstorms, they tend to be more scattered in nature. They develop in warm, humid air masses not associated with frontal boundaries. They're usually short-lived and rarely produce strong winds or hail, and generally air mass thunderstorms rely on the heating from the sun to fuel them. So air mass thunderstorms, I want you to think more of the summer season, when you get those, the morning time may be sunny, and then as we go into the afternoon, thunderstorms develop, and they're really quick in duration. You get really heavy rain, gusty winds, some vivid lightning with air mass thunderstorms in general. Again, they rarely produce severe weather as far as strong winds or hail, or they very rarely produce tornadoes, air mass thunderstorms. It's just the way the atmosphere is redistributing heat in the vertical when we talk about air mass thunderstorms. A very hot surface area, cooler air aloft, and the vertical air currents, those convective currents, are established. And once the thunderstorm reaches a mature stage, it dumps out a lot of heavy rain, and cooler temperatures are drugged down from aloft to the surface. And you might see with air mass thunderstorms, the temperatures drop on the order of 15 to 20 degrees during the mature stage. Severe thunderstorms, on the other hand, these are the ones that produce the most damage. These are the ones that produce the tornadoes. flash flooding, damaging large hail. And supercells are a special type of severe thunderstorm that are responsible for this large hail. Rotating updrafts, those mesocyclones, as well as tornadoes. Now, severe thunderstorms can occur at any time. These are dynamically driven storms. They occur both day or night and are more dynamic in nature. So when I'm talking about severe thunderstorms, I'm most likely looking at an area in association with a strong front, a large temperature contrasts, strong upper air disturbances up at 18,000 feet above the ground, these shortwave troughs, and jet stream. The jet stream sitting up at about 300 millibars or 30,000 feet. Maybe you're in one of those divergent, upper-level divergent quadrants of a jet streak. So let's first hone in on air mass thunderstorm characteristics. Again, they form in warm, humid air. You go outside on a hot, humid summer day, it feels really sticky. You start sweating real easily because the air's so humid. Temperature of 90 with a dew point of 73 or 74 degrees Fahrenheit. Okay. There's a lack of wind shear. There's a lack of wind shear with these, okay? So just wanted to point that out as well. Typical late afternoon with these type of storms, these type of air mass thunderstorms. They form at late afternoon and early evening. They form as parcels of air are lifted from the surface and along shallow convergence zones as well. You can get air mass thunderstorms along the sea breeze boundaries where you have a much hotter land surface as compared to the nearby water, and the wind blows in from the water during the day. Air rises over the heated land, and you can get these scattered air mass thunderstorms develop due to sea breeze effect. Topographic irregularities, as well as these sea breezes, and cold outflow of air from inside a thunderstorm that reaches the surface and spreads out horizontally, where you have outflow boundaries. That's an interesting thunderstorm phenomenon that I'll talk about more detail soon. Contrasting air temperature and humidity, air density result along convergence zones in general. All right, so if you look at the bottom, let me get my laser back out here. If you look at the bottom right picture here, it's not exactly blown up very largely in size, but in general, I'm showing you an example along the Carolina coast of a sea breeze. And what you'll have is the cooler air comes in off the water, the land is heated, and the air rises over the land, the wind comes in off the relatively cooler water, and it results in these cumulus clouds that develop. And as the afternoon wears on, sometimes these cumulus clouds can grow very tall vertically and form thunderstorms. Now, as far as air mass thunderstorms, they have a traditional life cycle. So I'm going to cover that now. We'll start off with the first stage of an air mass thunderstorm, and that is the cumulus stage. This is the first stage of growth as a parcel of humid air rises. It cools and condenses into a cumulus cloud or a cluster of cumulus clouds. And as the cloud vertically builds, the transformation of water vapor into liquid, that conversion of a liquid or a water vapor to a liquid, releases that latent heat of condensation. That further enhances the instability inside the cloud. The air wants to continue to rise, and the cloud continues to grow vertically as long as it is fed by rising air from the surface. Now, during the cumulus stage, updrafts tend to dominate, keeping water droplets and ice crystals suspended up within the cloud. And during the cumulus stage, there's usually no lightning or thunder heard. Here's an example of the cumulus stage. And you'll notice these red arrows. Now, these red arrows denote updrafts, or rising air within this developing cumulus cloud. Notice the puffy nature of this cloud. It's a cumulus cloud. And so the base of this cloud is sitting at about 4,000 to 5,000 feet above the ground. And now the cloud top is sitting around 20,000 feet. Another important part of this cloud is where the 0 Celsius line is, this pink dashed line. This represents your freezing level. So typically anything above this pink dashed line, the freezing level, you're typically going to get more in the way of ice crystals. You'll get liquid water droplets in the lower portions of this cumulus cloud as temperatures are above freezing there. But generally, cumulus stage, think updrafts, rising air motion. As the cloud builds above that freezing level that I just showed you, cloud particles are going to grow larger until the updraft can no longer hold them up, and water droplets and ice crystals will begin to fall out of the cloud due to greater density. And while this occurs, drier air from around the cloud is being drawn into it in a process that's known as dry air entrainment. Now that process, dry air entrainment, is going to cause some of the raindrops to basically evaporate, which tends to cool the air, and that when the air cools, it tends to become heavier and begins to descend from the cloud to the ground. And this really results in the formation of what's known as a downdraft. And again, think about as you're watching a line of thunderstorms approach your area, the wind begins to pick up. Think about how cool the air feels as that wind picks up. Most likely what you're feeling is that cooler downdraft wind coming out of the thunderstorm. All right? Now let's move on to the mature stage. In the mature stage, the appearance of the downdraft begins. Remember, the cumulus stage has strictly updrafts. The mature stage, I now have both updrafts and downdrafts. And during the mature stage is when that thunderstorm is most intense. If the cloud grows tall enough, its top may reach the stable stratosphere, which will act as a cap or lid, producing a flat anvil shape to the thunderstorm cloud. Upper level winds generally spread the cloud's ice crystals out horizontally. The downdraft and the updraft within that mature thunderstorm constitute what's known as a thunderstorm cell. You'll hear the TV meteorologists talk about cells, thunderstorm cells developing. And usually you'll see multiple cells which last for about an hour or so. And during the mature stage, the cloud may reach as high as 40,000 feet in the atmosphere. And updrafts and downdrafts tend to be the strongest in the middle of the cloud. And this creates an area of severe turbulence. This is an area where pilots want to avoid. Now, sometimes the updrafts can be very strong, and that still allows for penetration of the updrafts into the more stable stratosphere. This is a case that's known as overshooting tops. Lightning, thunder, heavy rain showers, and gusty winds are quite common during the mature stage. And once that colder downdraft comes out of the base of the thunderstorm and reaches the ground, it spreads out horizontally in all directions. The surface boundary that separates advancing cooler air from the surrounding warmer air, that is something that's known as a gust front. So here's an example of the mature stage of a thunderstorm, an air mass thunderstorm. Notice how I have some of these yellow arrows pointing upward. These are my updrafts. This is my updraft side of a thunderstorm. And then the yellow arrows pointing downward, that's the air descending, that cooler air descending out of the thunderstorm. That's where you're going to have your heavier rain. That's where you're going to feel that cooler downdraft breeze. And again, with some of the stronger downdrafts, you can see temperatures drop on the order of 15 to 20 degrees Fahrenheit. So it's really impressive. Ahead of this storm, it's very muggy, very hot and humid. But once the mature stage is reached, where you get these downdraft, you feel the downdraft portion of this thunderstorm cell, that's when you're going to get the heavy rain, the gusty winds, and the temperature is going to drop fairly drastically. Now look at the mature stage of this example. Now our cloud top is over 40,000 feet above the ground. See how much taller this is now as compared to the cumulus stage? See the cumulus stage just developing? And now the mature stage, much taller cloud. Updrafts and downdrafts, most intense portion of the cycle of the storm. So after the storm reaches mature stage, it will tend to dissipate in about 15 to 30 minutes. What's going to happen is these updrafts are going to be choked off, and the fuel for the storm, the warm, moist air from the surface on this side of the storm, is no longer going to be available. So during the dissipating stage, we go strictly to downdrafts, and that is basically going to destroy the necessary circulation, that vertical convection that's needed to keep fueling the storm. So the dissipating stage occurs when the updrafts weaken, the gust front moves away from the storm, outward away, and at this stage, downdrafts dominate. And they cut off that warm, moist supply of air that fuels the storm. Now, light precipitation may still be falling from the cloud at this point, but it'll be much lighter than the mature stage. And as the storm dissipates, the lower level cloud droplets evaporate rapidly. In some cases, you only see a cirrus anvil shape remaining aloft at the top of the cloud. Here is the dissipating stage of an air mass thunderstorm. Notice how it is just dominated by downdrafts, these downward directed arrows. And so this storm is pretty much dissipated. And you may still see that ice crystal anvil shape up here with these high above the top in that thunderstorm cloud. All of this is drying out towards the low levels of the atmosphere. So therefore, you lose that evaporation and you lose the moisture source. Generally, an air mass thunderstorm life cycle usually occurs, it lasts about an hour or less. These type of storms produce precipitation for a large portion of the United States, and they do offer that temporary cooling on oppressively hot, humid summer days. It feels great out there when you feel that downdraft kind of come in and drop the temperatures. Now, once the downdraft reaches the surface, I mentioned this earlier about how far temps can fall. They might fall in the order of 10 degrees Fahrenheit in just a few minutes at a time. And that cooling effect, it's not going to last forever though, because as the thunderstorm hits the dissipating stage, the downdrafts eventually will weaken, and you're going to get the cooling effect quickly waning as temperatures tend to rebound or increase after the storm dissipates. In addition, you had all that heavier rain that fell during the mature stage of the storm, and that's once the sun comes back out, as that storm dissipates, the sun returns, it's going to pick up, evaporate a lot of that moisture from the grassy surfaces and the streets, and that's going to result in an increased low-level humidity of the air, a lot more mugginess to the air. You're adding more evaporation of moisture into the lower atmosphere. Now, as outflow boundaries converge from dissipating storms, new multi-cell thunderstorms may result. Okay? So if you have multiple outflow boundaries converging, you can get the generation of new storms. And I'm going to show you what that looks like here in a minute. So let's just imagine this line here represents a outflow boundary. Let's say it's moving this direction. Okay? That's from a storm here to the north. And then let's say I have another outflow boundary down to the south, and it's moving this way. All right? So these two outflow boundaries are moving towards each other. So I had one storm to the south here, that's dissipating. A storm to the north, that's dissipating. This cool outflow of air, these outflow boundaries, right at this point here where they meet, once they meet, that could result in a new low-level convergence area and the formation of new thunderstorms. Here are some examples of outflow boundaries, whether we're looking at a schematic here showing you, again, keep in mind that this gust front here is the boundary between cooler downdraft air and the warm, moist air ahead of the this boundary. This boundary is that gust front between the cool downdraft air and the warmer updraft air. Okay, so you kind of see in this particular schematic in the upper left how the updraft air is on the right side of the storm, and then you have downdraft air on the left side, the cooler downdraft air. You also see where the rain is. It's in association with the cooler downdraft side of the storm. In this case also, we're getting an anvil shape up to the top here, and then we're also getting these overshooting tops, which indicates very intense convection and very intense updrafts to be able to punch through the stable stratospheric layer. On the bottom left, I'm showing you a satellite image of what an outflow boundary looks like. Generally, you kind of see what it's pointing to. It's like this arc-shaped cloud. That's an example of what an outflow boundary would look like on a satellite image. And then on the upper right, I'm showing you an actual, this right here would be a Doppler radar image showing the outflow boundary here represented by this green coloring. If I put this into motion, you'd see this gust front or this outflow boundary propagating outward away from the center of the thunderstorm. So it's important to note where these outflow boundaries are. You can see them on Doppler radar, you can detect them on satellite imagery, and just realize this is what's going on here. The outflow boundaries, once the downdraft air hits the ground, it spreads out horizontally in all directions, and that cooler, denser air eventually is going to flow outward away from the storm, and if it meets another outflow boundary, you can get renewed areas of thunderstorm development. All right, so now let's talk about severe thunderstorms. Now these are the ones that get the most attention, and rightfully so, because they can do damage. They can result in tornadoes that are on the ground for longer periods of time. Severe thunderstorms tend to form in a more dynamic environment. So air mass thunderstorms do not have the wind shear. Vertical wind shear is usually present in severe thunderstorms. And what you get with wind shear is a strong wind directional change with height in the vertical, as well as a strong turning of the winds with height due to wind speed differences between various layers as you go aloft. Unlike air mass thunderstorms with low wind shear, where the rain falls strictly down into the updraft, cutting off the storm's source of energy, increased wind shear with severe thunderstorms pushes the precipitation downwind of the updraft. So the updraft is basically not impacted at all. There's no cool, rain-filled air that's going to basically cut off the updraft, as it would be with an air mass thunderstorm. It's common to see severe thunderstorms protrude well up in the vertical in the stable stratosphere. So you see the overshooting tops most likely with severe thunderstorms due to intense updrafts. In some cases, severe thunderstorm cloud tops may exceed 60,000 feet above the ground. Look at this diagram here to the bottom right, showing a saucer-shaped pattern again. This is a very significant severe thunderstorm occurring, and most likely you're getting some type of rotation. This is very much the shape of a mesocyclone, a rotating updraft, rotating area. And the lowering of this particular cloud, this area here, the lowering of the cloud is known as the wall cloud. And the wall cloud is very important because that's usually the area you're going to look for a tornado or a funnel cloud to drop out of, from the cloud to the ground. And just to put this in simpler terms, to be considered severe, winds must reach or exceed 58 miles per hour, and you must see 1 inch hail or larger in diameter. Those are the severe criteria. And for ingredients for severe thunderstorms, I'm looking for the acronym SLIM. Shear, lift, instability, and moisture are all those ingredients present on a particular day. Vertical wind shear, again, is just a change of wind direction and speed with height. It's usually found with a strong low-level jet at about 850 millibars or 5,000 feet, overlaid by a change of wind direction and speed with height up to the 300 millibar level or 30,000 feet. And that creates those rotating updrafts, those mesocyclones. And then CAPE. That's a very important factor when we want to look to see if we're going to get severe thunderstorms. That has to do more with the lifting aspect. How much available potential energy is there in the atmosphere on a particular day? This describes atmospheric instability, and CAPE will also approximate your updraft strength of a particular thunderstorm. Instability and moisture, also very important ingredients to get severe thunderstorms. Low-level heating beneath colder air advection aloft, so you have that cow, colder air over warmer heated land. That's going to steepen lapse rates. That's going to enhance instability. And then if you get a lot of moisture, you get these extremely high surface dew points, just some juicy air mass. A lot of moisture. That moist air is also much less dense than dry air, so it's going to want to have more positive buoyancy. The air is going to want to rise more readily when it's hot and moist. All right, so that's going to provide, that moisture will provide that additional fuel source for a severe thunderstorm. And then you want a right balance of CAPE, the convective available potential energy, the vertical lift, the vertical motion. You want that right balance between the CAPE and the shear. The shear or the turning of the wind in the vertical with height. That's known as storm relative helicity. That's one of the most important things to take a look at on a particular day. Looking at a 0 to 6, the surface to 6 kilometers above the surface, that particular area, to see what that turning of the wind looks like. What's the vertical wind shear doing to any rising updrafts? Due to its very strong updrafts, large hail tends to form with severe thunderstorms, and those updrafts are so strong that they allow the hail to grow to larger and larger sizes. Severe thunderstorms have what's known as tilted updrafts. That's very important. The updraft and the downdraft regions are completely separated from each other, and rain tends to fall downwind of the updraft, again, not choking off the updraft at all. And one type of specific severe thunderstorm that's very special and very dangerous is what's known as a supercell. Now, this is an enormous rotating thunderstorm. These are the type of storms you'll see storm chasers out in the southern plains in their vehicles going to take video and pictures of. This is where you'll see your scientific research teams, such as when they were running Project Vortex, to go out and collect data on these particular supercell storms and tornadic development. You get rotating thunderstorms with these supercells. The updrafts and downdrafts are structured so that the storm is able to maintain itself for hours. In fact, I saw recently, I was paying attention to the Doppler radar a few weeks ago here in Virginia. One thing that's really struck a major note in my mind was the fact that we had supercells that night, and even after the sun went down, even after sunset, these thunderstorms, these supercells, are self-sustaining. They maintain themselves for hours. They don't necessarily need the heating from the sun to survive. They're really more dynamically driven with jet streaks at 300 millibars, with a very strong short wave at 500 millibars, a very strong area, positive vorticity advection, upper level divergence ahead of that shortwave trough. You're removing mass aloft over the low level convergence. You're looking at the wind shear is there with the jet stream. In a lot of cases, you have a strong low level jet. Updrafts with these supercells can exceed 90 knots. That's how strong and intense the updrafts can get. And hail can grow to the size of grapefruits. Damaging surface winds are quite common with supercells, and you get large, longer track tornadoes, unfortunately. Strong vertical wind shear, both directional and speed shear, occur, and in a lot of cases what you'll see is a southerly wind at the surface, 30 miles per hour or greater, and then maybe you have a westerly wind at 50 miles per hour or greater at 5,000 feet, and that causes this horizontal spinning between the vertical layers. An updraft can then tilt this horizontally spinning tube into the vertical, causing it to rotate. Supercells, again, can occur during the day and night, even without heating from the sun. That's the most impressive part of supercells. Now, I just wanted to kind of briefly cover the differences here, wind shear. Okay, so let's say this is the surface, and let's say my wind is from the southwest at about 30, I'll say 30 miles per hour in this case. Above that, at let's say 850 millibars, the second horizontal line here represents 850, I have a westerly wind at 60 knots. Okay? That's 60 knots at 5,000 feet or 850 millibars. So anytime I get an updraft through this kind of turning of wind direction with height and speed, in this case, I have both wind directional shear as well as wind speed shear. I'm going from 30 knots at the surface to 60 knots at 5,000 feet above the ground. Okay? What this is going to result in, look at the turning of the wind from southwest to west. That's a drastic turning of the wind. What that's going to result in is a horizontally rotating column of air in between the surface and 850 millibars. Now, it doesn't have to be strictly between the surface and 850 millibars or 5,000 feet. It could be in layers even a little bit higher than this, 5,000 to 10,000 feet, for example. But the overall thing I'm trying to point out here is with strong vertical shear, directional and speed, you're going to get some sort of rotation between these two layers. So that's what I'm trying to draw here, is just this horizontal spinning of air. And if you get an updraft now to move in the vertical, it's going to lift this horizontally spinning tube of air between the surface and 5,000 feet due to the strong vertical shear. It's going to push this horizontal spinning tube into a vertical position. and that is when you're going to see your funnel cloud develop. That's when you're going to see the funnel cloud drop out of the base of the wall cloud of a severe thunderstorm, and once it reaches the surface, it's no longer a funnel cloud. Once it comes in contact with the surface, it's now a tornado. Okay, so I wanted to point out how the shear is such an important factor that delineates severe thunderstorms, specifically supercells, versus air mass thunderstorms, which you see on a typical summer day. You don't have this kind of wind shear. You don't have these kind of jet dynamics, any kind of dynamics. The short wave at 500 millibars or 18,000 feet, it's not necessarily there with air mass thunderstorms. Those air mass thunderstorms rely on the heating of the sun to survive. The supercell thunderstorms do not. They do not rely on it. Additionally, you have a very strong frontal system coming into the area, very deep area of low pressure. You might have already reached the point of occlusion. It might be an occluded surface low. You got a lot going for you when you talk about supercells as compared to air mass thunderstorms. Here is some of the differences. I wanted to point these out here. These are the differences between the different wind profiles in the vertical from the surface to 30,000 feet. We talked about unorganized convection. That actually probably should be convection there. Apologize for that. But unorganized convection here on the left. And these are your winds with height. The wind direction and speed with height. So these could be your single air mass cells, your air mass multi-cells. The winds are much lighter over here on the left in the vertical, if you notice, okay? And the directional shear really isn't there. Now compare that to this more organized convection, where you can get squall lines, which I will talk more about soon, and when we talk about thunderstorm training, and then supercells. Now look at this difference on supercells. Now keep in mind that a flag is 50 knots of wind. A full barb is 10 knots. Look at how the direction of this wind changes from the surface, where the winds are southeast at 20 knots, and let's just say this is 5,000 feet or 850 millibars. I get a southwesterly wind at 45 knots at 5,000 feet above the ground. Look at the directional shear here between these two layers, the surface and 850 millibars. And then look at the wind speed increase up to 50 knots now at 10,000 feet or 700 millibars. And then all the way up to 30,000 feet where the jet stream is, 300 millibars, I have a wind at 90 knots blowing overhead. So you can see the difference in the vertical profile of wind with a supercell. This is a type of severe thunderstorm that can produce tornadoes, large hail, mesocyclones, and then over here on the far left, this is your typical summer afternoon day where you get scattered air mass thunderstorms that pop up. Your wind speed, your wind directions, your vertical shear just isn't very strong at all. This is not dynamically induced at all. Air mass, unorganized convection. Organized convection on the right here, whether we're talking of squall line, an approaching strong cold front, or whether we're talking about these supercells. I wanted to show you the drastic differences in the vertical with the wind directions and speeds on this particular graphic. And then look at the structure of a supercell. Okay, there's a lot of different parts of this structure. Supercells are very unique in that you see a more tilted updraft. Okay, so you're keeping the updraft portion on the left side, the lower left portion of this diagram. You're keeping the rotating updraft section, the strong updrafts over here, this tilted updraft, separate from these downdrafts. You got the forward flank downdraft, and then you got this very strong tilted updraft with the cloud tops overshooting into the stratosphere. Okay, you got this characteristic anvil. You get a good outflow aloft over this thing, and you get rotation. You get mesocyclones, rotating updrafts. These are very dangerous. And by the way, you can get rotating updrafts too, not only with supercells, but also with landfalling tropical cyclones, especially on the northeast quadrant of landfalling tropical cyclones, as the accelerated movement of the storm, as well as the wind, is strongest to the right of the track of the hurricane. The combined turbulence and general friction as that tropical cyclone moves over land, it tends to create major vertical wind shear. And so you can get quick spin-up tornadoes even in landfalling tropical cyclones in that northeast quadrant. But this is just a great example. This is a beautiful looking structure here. Again, the updrafts and downdrafts are separate. There's no downdraft choking off this updraft. Okay? And that's the big difference. Here is an example of a horizontal rotating tube on the left. Now these winds vectors, I call them vectors, these arrows. The shorter the arrow, the less the wind speed. The longer the arrow, the greater the wind speed. So now if this was the surface and we're going aloft into the vertical above the ground, notice how your wind speed continuously increases with height. And so this would be an example of speed shear, right? There's no changes in the direction of the arrow, so the wind is generally coming from the same direction at all levels, but you do have some drastic changes in wind speed as you go aloft. And that shear of any sort, in this case speed shear, can cause the air column to rotate in between two particular vertical levels in the atmosphere. And that rotation in the horizontal, if you get a strong updraft, again, let me focus this, let me really emphasize this, it's very important in the training. You get a strong updraft, which comes in here now, you have a horizontally rotating tube, and then you get a strong updraft like this, that tube, that horizontally rotating tube, is eventually going to rise up in the vertical like that and rotate right on down to the surface. You have this rotating column now, rotating from the cloud base to the ground, and then you get the development of a tornado. Okay, and then this just shows you, this graphic on the right shows you a more further explanation, detailed explanation of what's happening, where you get wind shear, fast-moving air streams, and then you get the horizontal spinning tube, and there's that updraft I was talking about, remember? That's what I'm trying to really emphasize here at point 2. You get a horizontally rotating column of air induced by this directional vertical wind shear, and then it's eventually an updraft is going to lift that horizontal rotating column of air, and eventually you get the rotation and you get a mesocyclone, rotating updraft, and this will eventually potentially reach the ground in the formation of a tornado. And then to end today's training, I just wanted to briefly cover, there are 3 supercell types of interest. We start off with the high precipitation type. This is going to produce extreme downdrafts. High precipitation supercells produce flash flooding on short order, very large hail. And the scariest thing with these heavy precip supercells is tornadoes are very difficult to see, as they can be wrapped into the rain, into the heavy rain. So you may have rain falling really heavily and you can't see the funnel cloud, you can't see the tornado. In this case, with high precipitation supercells, the upper level storm relative winds are 35 knots or less. So high precipitation supercells, you're typically going to find them east of the Rocky Mountains, especially as you get towards Dixie Alley. That's Mississippi, Alabama, Georgia. I've actually nearly experienced a tornado. I was driving to work one morning, and it was just a crazy torrential downpour in South Mississippi. So bad that my wipers were basically ineffective on the highest levels. I had my wipers on the highest speed possible. Still didn't matter. Anyway, I had to pull off the side of the road, and oh my goodness, I felt the car shake a little bit when I was in it. And sure enough, this particular high precipitation supercell, it dumped 7 inches of rain in 1 hour. And then I found out that there was actually a report of a tornado nearby. So I was very fortunate that particular morning driving to work. The rain was so heavy, so dangerous to even be able to pick that up. Another case, I was in the Florida Panhandle, and when another case of a rain-wrapped tornado occurred, and had to evacuate where I was located at the time. But it was just another case of a tornado being rain-wrapped. So when I look for rain-wrapped, I'm looking in the deep south, really. That's a very highly prolific area for these high precipitation supercells. Low precipitation supercells, on the other hand, as the name implies, associated with little precipitation, These are capable of producing tornadoes as well and large hail. Strong winds in the upper levels of the storm tend to evacuate the mass flux of precipitation far away from the updraft. Low precipitation supercells, think about more drier areas of the United States where these may occur. Then classic supercells occur where the upper level storm relative winds are between 40 and 60 knots. And by the way, these classic supercells can actually transition into HP, high precip supercells. There's a clear separation between the updraft and downdraft regions, as is the tilted updraft. So the common theme for supercells, that separation between updraft and downdraft regions and the tilt to the updraft. All right, that wraps up today's training, 12A, How the Weather Works training series on thunderstorms. We covered a lot today in the training. We started off with a discussion of thunderstorms in general. How do they form? Through the active convection, vertical transport of heat and moisture in the atmosphere. Triggers for this type of upward moving air or convection in the vertical include unequal heating of the surface. Terrain can also result in these air mass thunderstorms to develop on a hot summer day, or the lifting of air along frontal boundaries. We also talked about generally, like in the West Coast, for example, you can actually get thunderstorms to develop with lower surface temperatures, where you get these cold upper level lows that rotate into Southern California, coming off the Eastern Pacific, and these cold pockets of air in the upper levels. With the sunshine out heating the surface, you get a cold over warm situation, and that's an unstable situation where you're going to set up vertical air currents of convection. In general, that can happen as well. We get very showery lightning and thunder, showery precip, and sometimes you can actually get small hail associated with these cold upper lows as they move into Southern California in the winter season. Additionally, you can get thunderstorms to occur during snowstorms, believe it or not, when you get cold air aloft moving in over an area. You get a very deep, intense cyclone in the mid-latitudes in the winter season. And you also, whenever you hear thunder and see lightning with snowstorms, you generally tend to get the greatest forms of instability and the heaviest snowfall rates, by the way. Additionally, we talked about the two different types of thunderstorms, whether they be air mass, more scattered in nature, hot summer days, don't really produce much in the way of severe weather. They can produce strong gusty winds, yes. They can produce hail, but they generally rely on heating from the sun to fuel them. Now, severe thunderstorms, on the other hand, produce damaging winds, flash flooding, damaging large hail, and tornadoes. And we talked a lot about rotating updrafts with severe thunderstorms, more dynamically induced so they can survive even after sunset, self-sustaining. Whenever you get strong surface fronts, large thermal or temperature contrasts, strong short waves at 18,000 feet above the ground, as well as accelerated regions of wind speeds associated with the jet stream at 30,000 feet, these jet streaks, that can all result in producing a very dynamic situation in severe thunderstorms. Additionally, we delve a little deeper into air mass thunderstorms, generally associated with a lack of wind shear, typical late afternoon, evening thunderstorms in the summertime, especially down in places like Florida, where it seems like it's almost common every day to get an afternoon or evening thunderstorm. That's the type of air mass thunderstorm. That's generally caused by a sea breeze effect. Talked about outflow boundaries when you get cold downdraft air coming out of the base of a thunderstorm. Once it reaches the surface, it spreads out horizontally in all directions. Then I went over the air mass thunderstorm life cycle from cumulus to mature to dissipating phases or stages. And generally, these air mass thunderstorms last less than an hour overall. The dissipating stage, let's talk about some of the main features again in review. The cumulus stage is dominated by updrafts, rising air motions, convective currents. The mature stage, the most intense stage of the thunderstorm, it involves both updrafts and downdrafts. And that downdraft and updraft side by side, that constitutes a thunderstorm cell during the mature stage. And generally, the cloud may reach 40,000 feet in height or higher. With air mass thunderstorms, additionally, when we get to the downdrafts, dissipating stage. This occurs when the updrafts weaken and the storm is predominantly influenced by downdrafts. And then we talked about additional considerations with air mass thunderstorms. We talked about at times you can get these gust fronts or these outflow boundaries. Outflow boundaries moving away from dissipating thunderstorms to converge, and the formation of new thunderstorms can result. Here I showed an example of what a gust front or outflow boundary generally looks like on a weather radar, Doppler radar. Here at the bottom, you notice the arc shape to it on satellite imagery. Generally, that gust front is a dividing line between cooler downdraft air and the air ahead of it, the warm, moist air ahead of it. And then I talked about severe thunderstorms to conclude today's training. We talked about vertical wind shear being very important in the development of severe thunderstorms, strong turning of winds with height. In general, we get that intense wind shear tends to keep the precipitation downwind of the updraft out of the updraft core. So therefore, you get a unimpeded, strong updraft, not cutting off the supply of energy to the storm. And you can get cloud tops in excess of 60,000 feet. The top of the thunderstorm clouds tend to overshoot into the stable stratosphere with severe thunderstorms. The criteria for severe thunderstorms again, winds reaching or exceeding 58 miles per hour and or 1 inch of hail or larger in diameter. 1 inch hail or larger in diameter. And then the ingredients for severe thunderstorms. I'm looking for slim, SLIM, shear, lift, instability, and moisture. And we talked a little bit about those areas, and then I also talked about a special type of severe thunderstorm known as a supercell. These have rotating updrafts, mesocyclones. They're able to maintain themselves for hours. You get extremely strong vertical wind shear, both directional and speed, from the surface to aloft above the ground. A horizontal spinning tube between two layers of wind shear. You get a updraft to tilt that horizontally spinning tube into the vertical, and then you get the formation of a funnel cloud. Once the funnel cloud reaches the surface, it is officially classified as a tornado. And supercells can occur during the day and night. And then just a different profile, the winds in the vertical between unorganized convection and air mass thunderstorms to the far left, weaker wind speeds, less directional shear involved as we go up in the atmosphere as compared to these supercells. Look at the turning of this wind, and then look at the wind speed changes. A lot of shear in this particular graphic on the far, the supercells here on the far right-hand portion of the graphic for vertical wind profiles. You can get a lot of horizontal spinning air between the surface and this 5,000 foot layer in this case. And then here's the vertical structure of a supercell. Tilted updraft, downdraft, and updrafts remain separate from each other. Okay, you get heavy rain and large hail in the forward flank downdraft with the supercell, and then the mesocyclone, the rotating updraft, on the other side of the storm. And then just showing you some examples of a horizontal rotating tube. In this case, is due to wind speed shear, causes of differences in wind speed with height. And then the overall schematic here on the right, showing how that horizontal rotating tube at point 1 at the top eventually gets lifted into the vertical and forms this mesocyclone, rotating updraft, a rotating section of the thunderstorm, which can result in a funnel cloud and ultimately a tornado. And then the different types of supercells: high precipitation, low precipitation, and classic. And some of the main points with high precipitation supercells, very difficult to see, makes them very dangerous. You're going to be sitting there in an area of heavy rain, and you can't see where that tornado is located. Low precipitation, a little bit better. You get better visual. It doesn't have the precip there, the heavy precip. So you get a better visual of where the tornado is located. Think drier areas of the U.S. when we talk about low precipitation supercells. And then classic supercells is the third type of supercell. All right, everybody. Thank you so much for tuning in today for the training. Greatly appreciate it. I'm going to go into How the Weather Works 12B. That'll be the next video that I have waiting in the wings. We're going to talk more about thunderstorms in general. We'll talk about various elements of a thunderstorm. We'll get more into gust fronts. We'll get more into the types of clouds you see with thunderstorms, including shelf clouds, which are really cool. And then in How the Weather Works training series part 13, after the 12B thunderstorm training, I'll get into tornadoes. All right, so that wraps things up. I'll also be continuing my meteorology history series. I got Carl Gustav Rosby lined up, as well as Mr. Tornado, Theodore Fujita. Those are waiting in the wings as well. So that wraps things up today. Thank you so much for watching. Take care, everybody. And until next time, God bless everyone.